and I'm a prof in the Department of Earth and Planetary Sciences and also the Department of Physics here at McGill, and a member of the McGill Space Institute and other institutes that you don't have to know about. Okay, so my job is to introduce Lindy Elkins-Tanton, which is a great pleasure because she's an incredible person. So Lindy, okay, I'll give you the super short version because I was told to not make this super long. So she got a bachelor's in geology at MIT, then proceeded to have a whole career doing science publishing, having a kid, decides to go back to school, goes back to MIT, gets a PhD. A few years later, becomes a professor at MIT doing geophysics, then becomes the director of the Carnegie Department for Terrestrial Magnetism, Carnegie DTM, for those of you who know what that is. Kicks some ass and takes names regarding sexual harassment while at Carnegie DTM, then goes to be the director where she is now at Arizona State. She's the director of the School of Earth and Space Exploration, becomes the PI of the Psyche mission, which you're going to hear a good deal about tonight, so I won't tell you any more about Psyche, but is also involved in a whole slew of interesting initiatives ranging from astrobiology to education and all sorts of really cool stuff. That's all I'm going to say. So without further ado, please help me welcome Lindy Elkins-Tanton.
How's that? Is the volume good? I'm not too like spitty and up close to the microphone? Okay, good. Okay, hang on. No, don't ruin it. Wait. Don't ruin it. It's a surprise. I don't want them to know what's about to happen. Alright, so, sorry. I'm just trying to get this on my list. Here we go. I think that might have worked. We'll see. Okay. Ready? Didn't happen. No, it's not happening.
It's a shame, but living in the city, very rarely do you get to see stars.
It's totally not happening.
Like I have
Can you hit pause and go back? Ha 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 ha. You'll never guess. It's a video. We're about to show you a video. It's this thing we call the mission trailer. I know, this is just, there are too many buttons. So we made a 5-minute video about the mission, and we call it the mission trailer. And it turned out, I think, really nicely, and it's a nice introduction, and you get to see a bunch of the team members. We've got a great team. So that's what we're about to show you. We need to make sure the volume's high enough and that you can actually see the pictures. We did test this out extensively before you came. It's the green screen. What happened? This totally worked, you told me. Oh, do we have to drag it over? Oh, that's a good plan. So go out and then drag. Oh, it's on mirroring, so then you have to drag. I think you have to go out of, do you want me to do, you have to go out of full screen, and then you have to drag it over. Only we should like video mute so nobody sees the thing. Everybody riveted? You can hardly wait, right? So, oh, we're not going to know if it's right. Okay, you guys are going to see the whole thing. Yeah, totally. Okay, let's hit go. Ready to go? Here we go. Get the lights down. Get the volume up. A little louder.
It's a shame, but living in the city, very rarely do you get to see stars.
I feel like I have a new connection to them in a way that I haven't before.
From out in the desert and I look up at the sky, you just see millions and millions of places that we should be going.
Trying to make it louder.
It's almost baked into our DNA, the desire to go and explore, right? That's the whole reason why we left the forest and then traveled across oceans just to see what's out there.
I was born in 1969, which is the year we landed on the moon. So I am a space baby.
When I was a kid, there were guys driving cars on the moon. They're driving cars on the moon. That's so cool, right? I want to do that.
All the rocky planets that we know of all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field. But we don't know a lot about our core. What we've learned about it, we learn indirectly, because we can't go there.
It's too hot. Pressure's too high. Our instruments would melt. Can't drill a hole that deep in the Earth or other planets. It turns out we can study a planetary core out in space because there's this one object called Psyche.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
It is the only asteroid that we're aware of that is 95% metal or more and is really huge. It's about 200 kilometers across in one axis.
So it's about the size of Massachusetts.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
The first thing that came actually was the theory. Some people from Jet Propulsion Laboratory contacted me and said, we would like to plan a mission that would test your hypotheses.
And that starts you down a road that takes years. So we wrote a proposal to send a NASA spacecraft to visit this big ball of metal. And then about a year ago, Lindy gets a phone call. You win. And then we're all like, oh my God, now we have to do it.
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it will be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. So we talked with our mission design and navigation team, and in fact, they were able to come up with what is probably the most optimal trajectory, doing a Mars flyby.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
SSL is building the solar electric propulsion chassis. When we do the mechanical, physical integration of each instrument on the spacecraft, we'll work hand in hand with each of the providers to get out to Psyche and do a full discovery mission.
We've figured out a way for many, many people to build something together so complicated, no one person can understand it, but it all has to work together perfectly for decades without fail.
Just the fact that these things work at all is a thrill. It's just a testament to the engineers at JPL, the companies that we collaborate with, that they can build these things.
It's exciting for me to be able to be a woman winning and leading a deep space mission. The only previous woman who competed, won, and led a deep space mission was Maria Zuber, who is my friend and mentor at MIT. And so my drive is to make everyone feel welcome and to have every voice heard. We want as many undergraduates as we can. We want to involve as much of the public as we can. We want people to feel like this is their mission.
You get that first picture back, and one of the first things that goes through your mind is, oh, thank God I didn't leave the lens cap on. We will put our pictures out there as soon as they come down. So we'll discover the same time that the public discovers. We'll be scratching our heads and saying, I don't know what's going on. Same time everybody else is like, wow, what is that? I don't know, let's figure it out.
I did get to look at Psyche through an optical telescope in my backyard. Some wonderful colleagues brought over their telescope on a fortuitous night. It's a very, very tiny, faint dot. And that made a bunch of us cry to think that we could send something to investigate that speck of light.
We can understand this universe that we live in. We can explore it, we can learn about it, and we can be a part of something which is much bigger than just us or just this planet. We will see new things when we visit a world made of metal.
That's our mission trailer. So now you've got the whole overview, and I'm going to switch to the, oh wait, no I can't, yes I can, hang on. Switch to the PowerPoint. This was all supposed to be like seamless and beautiful, right? Or maybe I do have to do it kind of in front of all of you. Alright, never mind, all right, we get to watch it happen. almost ready. Are you ready? Here we go. And there we go. Okay, got it. So that's what we call our mission trailer. It kind of gives you an introduction to the team, lets you know a little bit about the process, lets you know a little bit about what the project is about, and so now you're kind of primed for walking through it in the PowerPoint slide version. And so this was the cover of our Step 2 proposal, and I'm going to come back to this in a little bit and tell you more about it. So this is the picture that you saw in that video. It's done by the same artist who did the picture you just saw, and it's just as much of a fantasy. It's based on scientific hypotheses that I think are as sound as any that we've got. But the one thing I can guarantee to you, and because this picture tends to get in people's heads, I just want to make it really clear this is not a photograph of Psyche. We have no photographs of Psyche, and I can practically guarantee you that when we get there, it will not look like this. Because the one thing that we find over and over again when we go to space is that we can think that we know a lot. We know a lot of theory, we know a lot of forward models, we've got some meteorites, but then when we get out there, it's not what we expected. It surprises us. And so I'm going to tell you the best things that we know right now today, and then when we get to Psyche, you'll remember and you go, she was totally wrong. Everything she said was wrong. Because that's what it is when you go out to actual nature and interrogate it directly. So this is how big the asteroid is compared to Japan, compared to Tokyo. Here it is compared to Massachusetts and Arizona. So as asteroids go, that's quite a big asteroid. When we get there, the spacecraft is going to be dwarfed by the giant size of the asteroid. And perhaps you noticed in that video, on the illustration where the spacecraft is coming into the asteroid and the spacecraft gets smaller and smaller. I actually had to fight with the engineers about this because they kept wanting to make the spacecraft look really big, and I kept trying to make the asteroid look really big. But the truth is that it's huge, and the spacecraft is really tiny compared to the size of this object. It's got a surface area much larger than California, so there's a lot of area to explore. And so, what I hope might be going through your heads is, you said this was mostly metal. Like, how could that be, and why is there only one of it? And so, let me tell you a little bit about the history of what we think this is. So this is just an Adobe Illustrator picture that I made around the time that we wrote that paper back in 2011 that caused JPL to say, let's test your hypothesis. And our hypothesis was about how very early in the solar system, bodies built up into what we call planetesimals, little planets, that were tens to hundreds of kilometers in radius. Now, that wasn't our idea. This is something that many people have recognized for a long time, and you can tell it's true from the meteorites that fall to Earth. So we know that within just 500,000 years of the very first solids forming in our solar system, bodies the size of Psyche and larger accumulated out of what was started out just as dust and heated up to the point that the metal that started out just intimately mixed with the rock, that the metal sank to the middle and made a metal core, which here is the gray material, leaving the rock on the outside. So that's a long sentence with a lot to parse in it if it's not your field, so I'm just going to go back a tiny bit. So we all know that inside the Earth is a metal core surrounded by rock. It's the same for the moon. The moon has a little metal core. It's the same for Mercury and Venus and Mars. And it turns out it was also true for these early planetesimals. So we have in our meteorite collection, which is, how many meteorite samples do we have on Earth now? Something like 60,000 meteorite samples, little shrapnel that has fallen from space. Some of it is just metal meteorites that we think came from the cores of bodies like this. Some of them are rocky, that seem to have come from the outsides. And then some of them maybe never melted, and they still have their metal and their rock intimately mixed. We can actually date these meteorites and know when these processes happened. So within 500,000 years of the first solids in the solar system, we had bodies like this. Now, our solar system, the first solids formed in our solar system 4.568 billion years ago. And so I used to tell my undergraduates, and sometimes I still do if I'm in that mood, that they have to memorize that number, and if they don't know that number at the end of the semester, they fail. So 4.568 billion years ago, that's the age of the first solids in our solar system. But if that was instead a 24-hour day, these planetesimals formed in the first 10 seconds. So really fast, they built up to be big objects that were very hot and ended up with a metal core. And so that's kind of the beginning of the Psyche story. You might kind of guess where we're going from here. So we imagine that there on the left, there's a kind of a bunch of planetesimals, and they all have got concentric rings like onions. So for a long time, people thought that the ones that didn't totally melt, they just formed a kind of an onion skin, an onion structure, where they're probably hottest, warmest in the middle, but maybe not fully melting, and fluids will kind of flow through them. But then other ones got hot enough to actually melt and form cores. And the way that we understood the solar system to form, now for a long time, although really its modern form of understanding was built up by a guy named Safronov, who was in Moscow in the 1960s. These planetesimals collided with each other, and they accreted together through gravity, and they built up to be bigger and bigger and bigger until finally we had our Earth. And so maybe you were taught in school, like I was, that the Earth was formed at a certain time, that you could say when the Earth was formed. Well, that is, not true, because in a sense, the Earth is still forming. We get meteorites and things from space all the time that are adding to our mass, and we lose mass. And that formation of the Earth, and we do count it from when it was 60% of the mass of the current Earth, and when was that? Maybe it's the moon forming impact. But we know for sure, we can put our finger on those first solids in the solar system and how quickly the planetesimals built up, then they collided and accreted up to the planets. One thing that was kind of neglected in all of this modeling for a long time is the fact that not every collision between two planetesimals makes a bigger planet. Sometimes they don't collide constructively, sometimes they collide destructively, and they smash each other apart. So Eric Asfog, who's worked on this a lot, says that perhaps half of the collisions in the early solar system were what he calls hit-and-run collisions, where two objects strike each other, and instead of merging together into a bigger object, they just knock some of the material off one of the objects, like a hit-and-run collision. So that's the leading hypothesis for Psyche, and you can see that on the lower path here. There's just like a little cartoon of a collision, and then all the rock is gone, and what you're left with is the metal from the middle, the stripped-off core. So in simple terms, that's our best hypothesis for how Psyche formed. So I have a couple of sort of stories to tell that come off of that concept. And the first one I want to tell you about is what we did with this idea when we're writing the proposal. I'm going to show in a few slides sort of what our process was to get to the point of winning this mission, because it's really been an incredible voyage, and it's a fun story to tell a little bit about. But one of the problems we realized early on, we worked on this for 6 years before we were selected for flight, and that's a pretty short amount of time in the mission world, 6 years. But as we're going through those 6 years, and the scientists are working with more and more engineers, and we're working with people who do the scheduling and the marketing and the finance and all this, we realized that they could never really understand why we were suggesting to bring the instruments we were suggesting to bring and make the measurements we were suggesting to make. And it turned out it was because we had this formation process for Psyche in our heads, which is kind of what I'm describing. Like, it builds up into a planetesimal. There's a series of hit and runs that knock the outside off, and then the middle was probably still molten, and then it's going to freeze. So we had this like videotape for how Psyche was formed in our heads that no one else had, because we hadn't shared that videotape. And we realized that we were going to have problems with the professional review panel from NASA, because they weren't going to have that videotape either. And we were not allowed to send them video links with the proposal. And although we could have them play a video to them at the in-person site visit, I wanted them to have a sense of what this was ahead of time, so they could understand the proposal. So we hired that same Hollywood artist who did the cover picture that you saw and that beautiful pretend Psyche to make the story of Psyche. And so he did. He made a cartoon series. So what is this a picture of right here? It's a hit and run collision, right? So now that we've sort of talked about it, you just totally get it. Let me ask a question. How many people here are Earth or planetary scientists of some variety? Most of the people that I already recognize who you are. And how many of you are not a scientist of any kind whatsoever? Awesome. I love it. Thank you for coming. And so here's what you need to do for me. When I slip up and I use some jargon or I say something that doesn't make any sense, will you please stop me? Will you be brave enough to say, I don't understand what you just said, could you explain it better? Because I'll do my best, but I really hate it when I'm trying to explain something and I know I'm losing somebody and they're not telling me. So be brave and shout out, like yell halt, and then so my husband is a math teacher. I'm sorry? Did you yell halt? No, okay, just checking. So my husband's a math teacher, and he used to try to get his students in college to let him know when they didn't understand something. And he said, okay, so when the time comes, when I say something that you don't understand, here's what you're going to do. And he goes, I guarantee to you, no one will notice. It'll just be between you and me, and I'll give you a little acknowledging look, and then I'll explain it again. So this only happened to him once in his entire career, and no one noticed. And he noticed, and he answered the question, and no one else even noticed. So little magic trick there. So here's a hit and run collision. You can see the object that's coming in, and it's striking the rock off of that molten metal core. Then what happens to that molten metal core? So here's where it gets really good. I'm about to tell you a little fable, like Aesop's fables. This one is based on the best chemical and physical modeling that we have and all the evidence we have from the meteorite collection. So it's scientifically very well founded, and I'm going to say again what I said before, it's probably completely wrong. But here's what you do, right? You make a set of ideas, a set of hypotheses that are well reasoned and well founded, and you understand all your assumptions, then you go test it. So that's what we're doing. So this is what we're testing. So here's a picture of the molten core that is becoming Psyche. It's freezing from the outside in. That gray stuff on the outside is the metal that's freezing against the coldest face. And then you can see some flaps of rock from the original outside of Psyche falling back down onto the outside of it. And then what's the purple thing? It's a magnetic field. Yes, so I'm here to tell you magnetic fields are purple. From now on, please draw your magnetic fields purple. This is like a Psyche characteristic. So these things that I just told you manifest in the meteorite collection someplace. There are meteorite families that show that they froze from the outside in. There are metal meteorites, many metal meteorites that retain a record of the magnetization that they got from their parent bodies. So we know that those parent bodies made magnetic dynamos. Do we know that this happened to Psyche? Absolutely not. We do not know that. But this is our best hypothesis. So then what happens next? It gets more exciting. So here's something about iron nickel metal, which is what we're pretty sure that this metal is, and also 90% of our Earth's core is almost certainly iron nickel metal, just like the iron meteorites that fall to Earth. It turns out that as it freezes into solid iron nickel metal from the molten form, it loses about 7% of its volume. So if it's freezing from the outside, it's made a hard shell against the cold of space, but then as the inside continues to freeze, it's losing volume, and the outside shell has to break and sink into place to accommodate that loss of volume. So that's why we're showing that there are cracks in there. There would be called contraction scarps if you want to impress your friends. And they can be seen, for example, on Mercury. Mercury has contraction scarps because it has a very big metal core that's been freezing over time and losing volume. So contraction scarps. And then another thing that happens while iron and nickel metal freezes is it excludes sulfur from the growing iron and nickel metal crystals, and so eventually it makes an immiscible liquid, a liquid that's mostly iron nickel metal still freezing, and a separate liquid that no longer mixes with it that's mostly sulfur. And so it's like oil and water in that case. They don't mix well. And so we hypothesize that that sulfur liquid, which would be buoyant, might squirt up through those cracks in the crust and make sulfur volcanoes on Psyche, which is an idea I just kind of can't resist. For those of us who are in this field, that's like, wow, sulfur volcanoes, oh my God. None of this is going to be happening now, of course. This all happened, in the first 3 minutes of the solar system, or the first 90 seconds, probably, if it's a 24-hour day. And so it's all cold and done now. It's no longer a heat-releasing planet the way Pluto still is heat-releasing, much to our thrill. But Psyche is really too small for that. So these are our ideas about what we might see when we go to Psyche. So this is the cover of our Step 1 proposal, made by the same artist. Now this guy, his name is Peter Rubin, and he is actually a professional Hollywood sci-fi artist. He created some of the ghosts in Ghostbusters. He designed one of the S icons for Superman, and he told me very proudly that in all time they've only copyrighted 5 of the different S's for Superman, and his is one of them. And he ended up consulting with us, and we paid him to make these illustrations so that people could understand. Why would we need to do this? Well, if you think about it, most missions are proposed to go to a place we've already been. We know what Mars looks like. We know what the moon looks like. We know what Saturn and Jupiter look like and what so many of these moons look like, but we do not know what a metal object looks like because we've never been close enough to see one. And so in order to engage the reviewers and show them what we think we're going to find, we needed a really good artist. And so that's Peter. So you can picture right here, this is the moment of the hit and run impact. Right now you can see that and see how that is. By the way, those cartoons I showed you a couple of showing the process, he actually made 60 of them, and then we made them both into flip books so that we could hand them to people and they'd get the video in their head, and into a video. And so you can see it on the YouTube channel for Psyche Mission, those cartoons telling the whole story of the formation of Psyche. So this was step one, and then 28 proposals came in for step one. These are all about 250 pages long. They cover every aspect of the mission that we're going to do, everything from building the spacecraft, which instruments, exactly what data they're going to take, what the data downlink rate is, how many people we need on the team, what it's going to cost every single month for the next 10 years. And out of those 28 proposals, NASA picked 5 to go forward to step 2. So that was pretty exciting. And so this one that I showed you before, this is our step 2 proposal cover. And now you know that this is about 30 seconds after the hit and run collision. So we're still trying to tell the story, tell the story, tell the story. So this is the way it went. JPL sent me that email back in 2011. Lindy, we want to make a mission, propose a mission to test your hypothesis. And there were about 5 of us then, and we started brainstorming about how can we learn about that first step of what's called differentiation, making a metal core and a silicate exterior. And finally we decided it had to be Psyche. And then we had to make sure, we had to confirm that Jet Propulsion Laboratory would sponsor our proposal. Cost a lot of money, a lot of people. Then we had to start adding people to the team, and this was my job as the principal investigator to build the team, and then eventually to choose an industry partner to build the spacecraft. And we had the wonderful luxury each step of this way of doing what we thought was exactly the right thing to do. You know, sometimes, and I know that we've all done this at one point or another in our lives in some way, you're making a decision between what you would do if there were no external pressures, the thing you thought was the absolute exact right answer, and then what you would choose if you were trying to befriend someone or not offend someone or pay attention to all the political pressures on the other side. But nobody expected us to win. And so we had this luxury of doing exactly what we thought the exact right answer was. So we chose SSL, something that used to be called Space Systems Loral, and then they became only an acronym, which is just so weird. A company in Palo Alto, they make communication satellites. They've got over 100 communication satellites orbiting the Earth, but they've never done a deep space mission before. So why would we select them to become a new NASA partner? Well, because they knew exactly how to build exactly the spacecraft that we wanted. They built it so many times that they could give us a firm fixed price. And their firm fixed price was so much lower than building it custom the way most NASA and all the big spacecrafts are built. They saved us $100 million and they broke the NASA cost model. And so we thought that that alone would make us never win because we thought we could not convince NASA that we were correct. So there we are making all the decisions we thought were the right decisions. And that was the partner RFI, request for information, in the beginning of 2014. When we wrote that first proposal, we submitted it in the beginning of 2015. And I can't resist, but because to me this whole thing is such a personal story that I will just add another thing in case it should ever be, I don't know, like good news or a nice thought for somebody. So right in July of 2014, I moved from Washington, D.C. to Arizona with my husband. And 6 weeks after I started the new job at Arizona State, which is a big job running this school, we in the last 12 months, our research volume was $53 million. And we have like 700 or 800 people in the school if you count the students. It's a big job. And 6 weeks after I started the job, I was diagnosed with ovarian cancer. Totally by surprise, no symptoms, like as usual. Super lucky in a really good statistical group, but I still had to go through chemotherapy. So I was absolutely, utterly sick all fall while we're writing our proposal. The proposal upon which over 100 people were already depending. Like, I wanted this proposal to win. I wanted us to go in strong. There were people who were spending $1 million, you know, between JPL and the industry partner and stuff. so when we handed in that proposal in January of 2015, I was still just unbelievably sick. So then we found out that we were one of the 5 to go on to the next step. And I felt so vindicated and excited. And so then we went on to write our step 2 proposal, the one with the 30 seconds after impact. So that one's about 1,000 pages. And by the time we got into 9 months into that year, then we had the site visit with the review panel in front of us, presenting all day. It's a long story. It was the absolute most high tension day of our lives for everybody in that room, including everything else, childbirth, marriage, illness, everything. Like, it was very, very intense. And then there I was, by myself in a little house in Western Massachusetts. My husband had gone to a math conference on January 4th of 2017 when the NASA administrator called me and told me that we won. And so it's very emotional. It's very personal for me. And the people that we've done this with, by the time we were in step 2, we had 150 people on the team. I mean, these people are like family at this point. It's unbelievable. So now we're actually doing it, and that's where we are now. We're in what's called phase B. And I will just say, also, like, as a little nice end to that story, I think about a week ago or 2 weeks ago, my doctor gave me my 5-year all clear, so I'm expected never ever to have cancer again, which is pretty awesome. And it kind of goes with the mission, right? It goes with the mission. So and I think it was the mission and the people and the job that I had that made me kind of pay no attention to that cancer. It was happening, or as little as I could, because I just had something much more important going on. And I know I'm talking to people in this room who've either been through this experience or your loved ones have been through this experience. And for me, it was having that thing that really mattered. And this was a big part of it. And so my husband and my son, who's now 26, have been very involved in all the steps and, coming to all the events. And it's awesome. All right, so selected in 2017. And then here we are here in the beginning of 2019. And notice that in the middle of 2019, or in another month or so, there's something called PDR, and then there's a line, and then begins phase C. So we're right now in what I've been calling tongue-in-cheek festive PDR season. So any of you who have been through engineering processes, there's a step, preliminary design review, where you need to show you've done all the work and you absolutely know how to build this thing and it's going to work perfectly, and you know all the numbers, you know every budget, you know every schedule, you know everything. Well, Psyche is a big enough mission that we have 18 PDRs, 18 instrument and subsystem PDRs leading up to the big project PDR, which is the second week of March. You can think of me then. 5 full days of stand-up presentation to a standing review board. And along with these 18 PDRs, they started in September. The most recent one was today, which I did not call into. And the next one is next Tuesday, Wednesday, Thursday. I'll go out to JPL and be on the board. That one's avionics. We also have 10 tabletops and peer reviews that go along. So that's why we call it festive PDR season, the season that just will not end. And so what will happen is, fingers crossed, after our big projects PDR, the second week of March, then NASA has an internal review, and then they make a decision. Key decision point C. And then they say, yes, we give you congressional mandate to go ahead and start building the spacecraft. And then we're in phase C, and we're doing implementation. You can see launch is August of 2022. I would like this to be the biggest launch party ever. I want it to be bigger than the Mars ones, even though NASA says that's not possible. I'm counting on you all to help me make it the biggest one ever. We think that the opening of the launch window is going to be August 6th, 2022 in Cape Canaveral, Florida. So please come, put it on your calendar. I'd like you all to be there. The reason that we can do all these things, like I can come and give you this talk, and we can hire the artist, and we can do this also carefully, and right now we're up to 500 people on the team, we're going to 600 or 700 people on the team, is that it's a big mission. So the PI managed costs on this mission is going to be about $760 million. And, it's a tiny, 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 tiny fraction of the money that we make as a nation in the United States. But to me, it is completely worth it because of the inspiration it gives to all of humankind to be bolder in our own lives. Because if we can do this, we can damn well fix what's going on here on Earth. We have the technology, we have the ability, we can stop being distracted, and we can get it right. And I think that's what space missions are for. All right, so what are we going to do when we go there? We're going to, of course, have to have a bunch of very clear and measurable science objectives so that the NASA administrator can go to Congress in the United States and say, yes, we have succeeded. You have to know what you're doing in order to assert that you have succeeded. And so these are our 5 big science objectives. First of all, determine whether Psyche is a core or is it something else. So every time I give a talk, everywhere in the world, over the last 10 years, I ask people, what could Psyche be if it's not the core of a planetesimal? People tend to agree, core of the planetesimal, probably the most likely thing. But what else could it be? Well, it's not the Death Star. And I learned that it's not the Death Star because it turns out the Death Star was quite a bit larger than Psyche is. So it could be a prototype. We're not going to know until we get there. It's so funny. Somebody always says, that's no moon. It's possible that it could be material that never melted, but it formed very near the young sun and had all of its oxygen driven out. Theoretically, that material could exist, but we have no examples of it ever. Or maybe it's something we just haven't even been able to imagine yet. And here's the great part. This is the part I love the most. So I told you about hit-and-run collisions. It sounds kind of facile. Hit-and-run collision, all the rock goes away. Well, the models say it takes between 4 and 8 hit-and-run collisions to knock all the rock off of a planetesimal core with no accretionary collisions in between. So it's like coin flip. It's like heads, 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 you're done. No tails ever. Statistically, this is not super likely. So when you run the coin flipping is not a good analogy because heads is as likely as tails. But you understand what I'm trying to say here. So when you run many, many examples of making a solar system, usually you end up with no Psyches in it, nothing that's a large metal body created by hit and runs. Sometimes you end up with 1, and every once in a while you end up with 2, so it's improbable. Now there is only 1 of these in our solar system. There are 9 other asteroids which seem to be made of metal based on their radar properties, but they're very small and kind of weirdly shaped, and they're not big, relatively round things like Psyche. So we have 1 Psyche in our whole solar system, that's it. So the most probable idea we have is that it's the result of 4 to 8 hit-and-run collisions. So improbable, but most probable. So Psyche, the ideas for Psyche go from the improbable to the probably impossible. We don't really have any really likely ideas for what it is and how it formed. So that makes me just really eager to go there. So is it a core is a big one. Then the middle 3 are all kind of technical objectives for people who are planetary science geeks and would be really interested. And then the last one is the one that I'm really kind of counting on for the world, which is characterized its topography. Usually you can't just write an objective that's totally open-ended like that, but the fact is humankind has never visited this kind of object before, and we do not know. And so here's a picture of Psyche from my backyard. That's one I talk about in that film. But even with the Hubble Space Telescope, it's only 2 pixels. Now we've got a pretty good shape model for it in terms of knowing its 3 axes pretty well. That's through radar reflection, which if you're into technology miracles, I think this is a technology miracle. You can take the Arecibo radar telescope and you can bounce radar waves off of Psyche and receive them again and build them up into a shape model. To me, that is a technological miracle. But it doesn't really help us with any of the fine scale, and it's only good to a certain amount of error. It doesn't give you color, it doesn't give you the fine shape or anything else. So this is kind of what we know about Psyche. That's what it looks like. Now, what's the number 1 kind of surface thing we're going to see on a body that has no atmosphere out in space? What are we going to see? Craters. We're going to see craters, like when you look up at the moon. Well, we've seen craters in rock, and we've seen craters in ice, but we have never seen craters in metal. So what do they look like? How do we even know about craters? So until not too long ago, most people thought craters on the moon were actually volcanoes because we had no experience of the very high energy physics that causes craters. People began to understand that, sadly, with the nuclear age, as we understood bombs. We still have never seen a hypervelocity impact into rock or ice, but we've got models that kind of model it and help us understand. So if you do a very high-speed impact, like with the Ames gun, into a little metal piece, it makes a crater like this. Now that little impactor in the bottom of the crater obviously is not the one that made the crater, which was destroyed by making the crater. It's just another one to show you the size. Now do you see how there are these ejectoflaps that stand up at the edges of the crater? When they happen in rock, they splash up because everything's been liquefied by shock, and then they fall back down again. You can see them, the rays of rock that are laid down on the moon around the fresh craters. When it happens in metal, sometimes they freeze before they fall down. So you wouldn't expect that to happen on a very big scale on Psyche, but it could leave things like turrets and points or weird kind of frozen tektite blobs on the surface of Psyche. So we're going to look for that. And we have it in that Peter Rubin image, because that image, the very first image where I was reminding you that we made it up, but it's all based on our science hypotheses. Peter Rubin and I Skyped on Sundays for about 2 years, so I could explain to him our scientific understanding and he could translate it. So there are sort of frozen turrets around the impact craters in his images for this reason. It's also possible that parts of Psyche are cold enough that when an impact hits it, it shatters like glass instead of flowing into a crater. That would be pretty cool. A lot of meteorites on Earth are pallasites. Not a lot. A small number of the metal meteorites that fall to Earth are these things called pallasites that have these beautiful rock crystals in them, in this case olivine. That could be what part of Psyche is made of. Psyche could be a giant pallasite, and it could look kind of like this if you could shave it really thin and shine the sun through it, which it wouldn't, but we could imagine it would look like that. So we don't really know. And what Jim Bell said in that video, so first of all, there's no lens cap, so we don't have to worry about that. So NASA allows mission teams to keep all the data to themselves for 6 months so that we can make up our scientific hypotheses and publish before giving it to the world. But we don't think that that's right. These are taxpayer dollars, but more than that, this is a human endeavor for all of humankind. I really believe that. And so we think we figured out a data pipeline. The data center for this mission is at Arizona State. We think we figured out a data pipeline that these images will be sent out on the web for free to everyone in the world within a half hour of our receiving them. And so keep your eye out. You'll be seeing it when we see it, seeing what this looks like. All right, so what are we sending? So here's the chassis of the spacecraft that Space Systems Loral, SSL, is making for us. It's basically a big cube, and you can see, if you look at the top left, there's a boom that goes up, and we've got a gamma ray and neutron spectrometer on there. So we were just talking about this before we started. Most missions have cute acronym names for all their instruments. They're called like Maxie and Fanny and Elsie and stuff like that, which I find super confusing because then I can never remember which one is the camera and which one is the blah blah blah. So we decided we're not doing that. Our gamma ray and neutron spectrometer's name is gamma ray and neutron spectrometer. And what that allows us to do is measure the composition of the surface on an elemental basis. We'll find out how much nickel and how much iron and how much aluminum, things like that. It's up on a boom so that the spacecraft material doesn't give too much signal. Then you can see, if you go over to the right, you can see another boom that's got magnetometers on it in what's called a gradiometer configuration, one farther from the spacecraft and one closer, so we can subtract from our signal the magnetic field of the spacecraft itself, which of course it has one. Then there's the imagers that are poking through at the back. And we're also hoping to fly deep space optical communication as a tech demo for NASA. This is a demo that will actually use lasers to communicate data back to the Earth instead of radio waves. And I will go on in geeky detail about that incredibly cool thing if you want me to later. This, if you look at the dimensions, is big, 2.4 by 3.1 meters, which means that we're actually building a life-size facsimile of the spacecraft in the vestibule or the lobby of our headquarters building at ASU. We figured it's a big, tall sort of gallery space, and we figured out that with the solar arrays deployed, we will be able to fit it in there at life size as long as it's tilted in a certain way. And so we have now the aluminum box outline of the chassis. So if I stand in it and put my hand up, I can just touch the top of it. It's big. And all of our instruments are on the outside. So why are we building this giant box to send 3 little instruments that are hanging on the outside? Well, the main thing that's going to be inside that box is 950 kilograms of xenon, the most amount of xenon that's ever been launched off of the Earth, because xenon is our propellant. This is a solar electric propelled spacecraft. Every little xenon atom is going to be ionized and then sent out through a field out of these little thrusters, Hall effect thrusters, lending its tiny bit of momentum to the forward thrust of the spacecraft. And the power we'll use to ionize them is solar power. So it's a very sustainable spacecraft. It can go off at slow impulse, but super high efficiency using only solar power for 10 years. But mostly inside that box is going to be empty space. So why would we do that? Well, it goes back to this firm fixed price thing. Turns out if we had them design and build the box that exactly fitted what we were trying to do, it would have been $100 million more. But because we asked them to build the smallest version of the boxes that they build every day, it's way cheaper. So I think that's kind of interesting. So then here's what it looks like with the solar panels out. It's the size of a singles tennis court. So it's 25 meters across with the solar panels out. And you can imagine then seeing them in those sections, how they fold up and stow flat across against the sides of the chassis until launch, and then they get deployed. At Earth, they're going to be about 20 kilowatts of power, and then as we get out farther and farther from Earth, of course, the power goes down. So here's what we're going to do. We're going to, you see where Earth is there. You can see we're launching in August of 2022. The blue dots are where we scheduled the deep space optical communication test. The red is checkout, and then the gray bands over the trajectory is when we're actually going to be thrusting using those Hall effect thrusters in xenon, and the no gray bands is where we're just coasting. You can see the Mars flyby in May of 2023, and then conjunction is when the sun goes between Psyche and us, so there's a period of blackout. And then we continue thrusting, and we go all the way around, and then up at the top of the figure, we see we arrive at Psyche in January of 2026. We don't actually know within a couple of days when that will be, because it depends a bit upon whether we thrust exactly as long as we expect, or if there's exceptions and things like that. Then we will orbit Psyche for 21 months. And during those 21 months, Psyche will go around the sun as far as it's shown in that orbit right there. And then where it says A, B, C, and D, we're going to be starting up high until we really know the gravity field. Then we've calculated a stable orbit will go down to B, down to C, down to D, getting closer and closer and closer and getting better and better data. And then we're done. We're done in October of 2027. So it's kind of a long endeavor. I want to tell you a couple of other things about what we're doing because I feel so strongly about this. NASA gave us the opportunity to propose a much more bold student collaboration than what other space missions have done. So we have Psyche Inspired, who are undergraduate artists who create art for us. And this is our second year of Psyche Inspired. Last year we got 50 original works of art. We put them up on our website, and we tweet them out, and we put them on Facebook, and they include original music. They include cross-stitch, chalk art, drawings, sculpture, ceramics. I mean, it's very, very, very exciting and fun. Then the Capstone Projects, we collaborate with universities all across the country. And in fact, we can, as long as there's no cost to us, also collaborate outside the country in case you'd like to do capstone projects here that are related specifically to real problems we're trying to solve in the mission. Last year, we had people make the first Psyche smartphone app. And it's in its final polish and is about to be certified by NASA and sent out. So that's kind of cool. Let's see. Then on the website you can get there are all kinds of models and materials that you can order or download. And then there are some careers and internship information. And in about a month, we're going to release our first of a series of free online courses. This one is going to be the lifetime of a space mission, how you go through the whole process I've been talking about all the way up to the end. And it's free worldwide forever because of NASA. And so you can take this course online and learn all the different details. And the next one that we're doing right now is called the Inclusive Mindset, which is about how to create a team of 500 people who work together well and where all voices are heard and people can succeed on their merits. And we're doing that with a subject matter expert of profound proportion. So that'll be our next free online course. We do, this is shown with permission of her parents. That is the other temporary tattoo, which sadly I couldn't bring because we're out of it, with a little metallic asteroid. We do a tremendous amount of speaking like this and go all over the world. A lot of the team members, you can get engineers to come up here and tell you all about the engineering. This is one of the ceramics. This guy, this is the second to last slide. I just have to tell you, this guy is an amazing ceramicist. And he took thermite, right? This is like basically explosive high heat steel melting material, and put it into the glaze of this to try to make something that would look like the surface of something metal in his imagination. And it caused such a high temperature in the kiln that the automatic shutoff happened, but luckily it didn't kill the kiln, and I didn't learn about this till later. But it is the coolest piece of ceramic. I'm kind of in love with it. And so finally, this is the last close-up by Peter Rubin with those sort of turrets maybe next to the edge of the crater, and there's our website and our Twitter, and I really hope that you'll stick with us and follow the mission and participate in any way that you would like to. So thank you very much for coming tonight. It's here. Let's see. Lights control. Okay, good. Nobody yelled halt, so I assume you understood every word. Yeah, yeah. Yes. Yes, pretty darn sure, says the scientist. So we actually can measure the density, but with some fairly large error bars, and you get the mass by faint interactions with other orbiting objects, and then you get the volume from the shape model. And it seems like its density is probably between 4,000 and 5,000 kilograms per cubic meter. If it was solid iron nickel metal, it'd be about 7,000. But if it was rock, it would be 3,500, and most rocky asteroids are down around 1,500 because they're broken into pieces. So that's evidence of high density. But the things that actually convince me are radar, are actually from radar. There is thermal inertia, that is how heat and energy move through the body, and then the albedo, how much is reflected, and they are both very, very different than rocky objects. And so there are about 9 other objects that seem to be made of metal, but they're just little scrappy shrapnel. They're not a big thing. So we're pretty darn sure it's metal. That's how. Yeah. Yeah, that's interesting. Some of the big things I mentioned, like breaking the cost model and choosing an organization, SSL, that had never partnered with NASA before, partly I would like to imagine that it was just our unbelievably compelling narrative in the proposal that we wrote. But the truth of it is that the selection official became the new NASA Associate Administrator, Thomas Zurbuchen, who comes from an innovation engineering background, where he is driven very much by what he sees in the proposal and understands to be true about the models. So it's not so much the tradition, well, why aren't you going with Lockheed, they do all these things. He saw the possibility for NASA to break new ground and make a new partner, and the fact that that was credible was really exciting to him. So in some ways we were just received well by people who wanted the changes we were making. And then the other thing that I did a lot, and I'm not saying that I did it super successfully, and God knows time will tell, but working with JPL to create a team that had a different culture than most teams. I really dislike the traditional kind of militaristic hero culture that has been prevalent in aerospace and also in academia, frankly. I really like a team culture where you're driven by a question or a project instead of an ego and a name. And so we specifically set up all of our team meetings so that everyone gets a chance to speak, and that if you're junior, it doesn't matter, you're senior, it doesn't matter, everybody listens, nobody yells at each other. And so I was lucky to get a project manager who was really willing to give this a try. And then in the end, the proof is in the pudding. So NASA told us that one of the reasons they selected us is because they could see at the site visit that we all were willing to listen to each other and pass the questions and answers off to whomever was actually the expert. They could see that we had a good rapport. They could see that under pressure we didn't break, and that actually helped them choose us. And then the other thing we've seen is that if things are, so just good news for all of you young people, it's very, very hard to get enough staff in aerospace right now. There are not enough programmers, there are not enough engineers, and we have had less trouble getting staffed than some other missions. We have people telling us, we hear you're good to work with, we'd like to be on your team. And so that's really great, and I'm hoping that it's not a myth and that we're able to perpetuate, because it really matters. Hard, culture is hard, but we've been proved right so far. It's nice. Yes. Yes, oh my gosh, we considered so many fantasy fabulous things like 2 CubeSats and landing, and Well, so, those of you who are in this field know that NASA is extremely risk averse. So when you say you're going to do something, you better be able to do it. And it turns out you cannot fly to the outer asteroid belt and land for $760 million. Now, JAXA is an amazing space agency in Japan, and they go for high-risk, super innovative things. So they land 3 things on their asteroid. I'd like to say we're certain we're going to do our modest mission. Yeah, that's it. So there are a lot of things we would love to do. And so in the end, our end of mission scenario is to go down closer and closer and closer and closer, but we're not allowed to say land. It'll land at the end. Yeah. There was somebody here. Okay, right there. Yeah. Yeah. The deep space optical comm with laser. Yeah, let me tell you in a brief nutshell. Has anybody here done anything with laser communications, by the way? It's like a very small field, but I think it's super cool. So it turns out you can send a lot more data in a laser. There are more parameters that you can alter to send data. So here's how this is going to work. There's going to be a laser in a telescope in California that's going to be big enough that it's going to send the laser all the way out to where Psyche is near Mars at that time. And Psyche's instrument is going to detect that laser. And then Psyche has a laser that it's going to send back to the Earth. It'll be so diffuse and low energy, won't hurt anybody. It'll be just like sunlight, so don't worry. And it's going to be received by a different telescope in California that is going to have a grid, like a matrix of many little mechanisms that can count photons. And these are called superconducting nanowires. They'll be held at about 7 degrees Kelvin, so that they're super cold, so that they're superconducting, such that the energy of a single photon is enough to warm them up that they stop superconducting and end the circuit, and then immediately get cooled down to be superconducting again. So this grid will count every single photon that comes from Psyche. And here's the last thing, which I find so, if you don't love superconducting nanowires, then seriously, get out of tech, because it's the coolest thing ever. But here's the other thing I love. It turns out the ability for the Psyche spacecraft to point exactly at the receiver in California is very, very, very good, but not quite good enough for this instrument. So it is actually going to be able to detach itself from the spacecraft and using magnets orient itself even more perfectly and then clamp back down. Which when people told me that, it was like, you are nuts. But now we agree. Okay. Yeah. So that's DSOC. Way in the back. It was discovered in 1852 by the chief astronomer in Naples, Italy. His name was Annibale di Gasparis, and the backstory of that is one of the best stories in all of science. In the late 18th century, there was what is it called, Bode's law, right? This law that they thought that they figured out an algorithm that explained the spacing, Mr. Bode, whoever he was, of the planets, and that there should have been one where the asteroid belt was. And so starting by this guy, Franz Xaver von Zach in Germany, he said, I'm going to form a group, and we're going to call ourselves Die Himmelspolizei, the Celestial Police. And our job is going to be to set rights to the heavens, to set them straight again, to set order to the heavens by finding the missing planet. And so he made a big coalition of astronomers all over Europe, and they started searching. So first in, 1806 or 7, somebody probably knows the number, they found Ceres, the first asteroid, and they found another one, and then eventually in 1852, they found number 16 Psyche. And at some point they realized there were only little things out there and no big planet, and the Himmelspolizei was dissolved. So the Psyche was part of that, and of course they named everything after the gods and demigods at that time. So that's how it got its name. Another question? So true. Yes. I love saying that, a naked core in space. And people go, what? Scandalized. So what do we learn? Yeah. Right. So It used to be, and maybe some of you were taught in school like I was, that there was something called the Iron Catastrophe, that the Earth basically formed, and then suddenly all the metal just sank to the middle in this giant catastrophic event. Totally fantasy, absolutely based on nothing. So it turns out that core formation is many, many, many steps, starting with these planetesimals that merge, and then their cores merge, and their cores merge over and over again until you come to the Earth. And so the Earth is one end of the story, and Psyche, we think, is the other end of the story. And so if you're familiar with this, with the German prefix or, like original or primal, like this could be the or core. Psyche could be an example of the very first time that a core formed in the solar system. Maybe, maybe not. If it's not, and it's still metal, it's one of that early generation. So that's a core that formed at very high temperature and low pressure. And it would be basically like the eggs and flour that ended up being the Earth's core. And so what we're going to learn from that is, what do you start with? We're pretty sure we know what we end with. And so then we'll be able to track much better the state of temperature, pressure, and oxygen activity of all those core forming events to get to where we are now. Everyone is silenced by superconducting nanowires. Yes. Yeah, right now all spacecraft are done with radio waves, and there are different bands. There's an X band and a K band and so forth. But radio waves, you can only encode information in a relatively simple way, so it takes more radio wave to give the same amount of data. With a laser, you have more parameters you can tune, so you can send more data. And so the idea is that, for example, I'm going to get the number wrong, so I'm not going to try to remember. I forget what the multiple of data rate is from the Mars distance, which is really what this is designed for, not from Psyche distance, where they're not that different. But from Mars, there's a big multiplication of data rate. So the idea is that when we send people to Mars, finally, we need to have a laser comm so that we can get a much bigger bandwidth. So that's the purpose. No, it's all speed of light. It's just, I'm sorry? Yeah, it's a huge data rate difference, right? So over the same amount of time, you get a lot more data. Yeah. Yeah, so it's just that there are more parameters you can encode. Last question. Yeah, in terms of what were the other proposals? An interesting thing is, a lot of proposal writers keep their proposals absolutely secret. There's this idea that that if you let other people know what you're proposing to do, that they could ghost you in their proposal and make their proposal look stronger than yours if they knew what you were doing. So, but we took the other point of view. We were pretty sure nobody else would propose to go to Psyche, and that in fact a lot of people had never heard of Psyche. So we thought we better start talking about Psyche a lot and explain to people how cool it was. And so we were very out there, so everybody knew we were coming. So we knew what some of the other proposals were, but not all of them. And in the end, I think we got all 28, but I'm not sure. The big thing was Venus. Everybody said it's time to go to Venus, right? Venus is Earth on a really bad day. And we do not understand why Venus is so different from the Earth. And so a lot of people thought, well, it's been a long time since we've had a mission to Venus. It's the most important planet in our solar system for understanding what might happen to Earth. We've got to figure it out. We've got to go. Come to find out, so everybody said it's Venus's year. It's going to be Venus. And if they picked two, which they did pick two, they picked us and this mission Lucy, which is going out to the Trojan asteroids, run by my friend Hal Levison. They said, well, if they pick Lucy, then the other one that they pick will probably not be a small planet, it's a small bodies mission, because they're doing some other small bodies missions. So we thought Venus was our big competitor. But it turned out that none of the Venus missions showed that you could make a huge leap forward in science for the cost of a discovery mission. There's another class of mission, bigger New Frontiers, and then there's flagship missions like the Curiosity rover, Mars 2020, Europa Clipper. Those are much bigger and more expensive than Psyche. So it would take a flagship mission to make a very significant step forward in Venus information, because we already know a lot about it. So in terms of science for the dollar, we ended up coming out way ahead, but everybody thought it'd be Venus. Yeah. Thanks a lot. I appreciate it.